Hello everyone. I hope you started a great day, and let's start our discussion for today's lecture. Today we are gonna start our last chapter, the last concept that we are gonna cover for the course Introduction to Control System. And basically, this is the frequency response of a system and how we can use techniques like Bode and Nyquist. We are going to use those techniques and how we can use them for analyzing the system, find out how would the system react to different inputs, and how we can basically determine if the system is stable based on those methods. Now, before I start the main concept, I wanted to actually talk about why actually we need to talk about this Bode plot or frequency domain, or frequency response, Nyquist. So far, we talked about the S domain and root locus, and we find out how we can basically analyze the dynamic of our system. Either way, if we have a static system or we have a system that has a variable in it, we learn how to do that. But most of the time, those techniques are useful when we are dealing with a transient response. So we have like a period of a transition between the two states, and we want to find out, okay, what's going to happen to our system. Now, beside that, in the beginning of the course, we said, okay, one of the other analysis that we have to do, and is one of the main concept of the analysis of the control system, or any type of system actually, is the steady state analysis. Is when we have any arbitrary input, and we already passed transition between the previous state and current state, and now we want to see what's going to happen in our system if we have such an input to our system. Now, I say arbitrary because, as you know, it doesn't matter what type of input we have a very good tool named Fourier transform that we could transfer any type of arbitrary input or signal or whatever you want to call it into a bunch of sinusoidal with different magnitude and different frequency. Okay, so taking advantage of that, basically it means when we want to run a steady state analysis, we can make our life easier, but only learn how to run an analysis over sinusoidal inputs. If we know how to work with the sinusoidals for steady state analysis, basically we're good to go for all the arbitrary input that we could have. Are we good so far? Now, in the previous sessions actually, when we talked about the root locus, we were working all over the S plane. Okay, and we know, yes, if we have a complex number, we are going to have an oscillation frequency. There is going to be oscillation in our system, okay, but it's not a sinusoidal, it's not a pure oscillation, okay. Any point in the S domain is not just a pure oscillation, unless it's exactly on an imaginary line. Okay, so the only condition that we saw before that we could have an exact and sustainable oscillation, which is having a steady state of sinusoidal, like with a sinusoidal frequency, or you know what I'm saying. So we have a sustainable oscillation, which we could, based on the Fourier transform, translate as a bunch of sine or cosine with different magnitude and different frequency, is when our S is gonna, our poles or the state of our system's dynamic would be exactly on an imaginary line. Okay? Now, the imaginary line numbers, we call them J omega. J for the imaginary, and we said, okay, whatever value of the complex number that we have, that imaginary part was our oscillation, was our oscillatory frequency. Okay, so when we are on the line, basically that means any point on that line is simply a sinusoidal or a sine cosine function with the frequency equal to the magnitude of that line. Are we clear what we're talking about, the statement? Is that fully clear, or there is any question on that? So before, if we happen to end up exactly on the on the imaginary line, then we said it's kind of like, we call it marginally stable, and we said, okay, on that point we have a sustainable oscillation. It doesn't go away, it doesn't increase either. Sustainable oscillation. Okay, so now if we wanted to like just only analyze those type of dynamic for those type of point, those type of state, meaning we wanted to only focus on on the imaginary line, why give us a headache of running the whole root locus or any type of like a time domain or estimate analysis to just find a very tiny portion of that, plane or that data that we get from the analysis. So now we move on to a new type of analysis, which we call it a frequency analysis or frequency response. And the definition of the frequency response is pretty much what we learned before. All the characteristics, all the rules and regulation are the same, what we learned from the root locus, but we are going to simplify it by simply making S equal to J omega. And that's it. So you have root locus. You already understand all the characteristics, like how the damping factor would affect, how the phase angle for the stability analysis would work, how, all those characteristics that we had for S domain. Now we wanted to like use the state domain, that S domain, for a specific steady state oscillation, and to do that is simply just S equal to J omega. Now, if we want to do that, one way is to go through the hell of like it wasn't hell, but it's a lot more kind of like process to run the root locus or any type of S domain analysis over the system and then make S equal to J omega, or we can simplify the process, okay, and have an easier life to find out what is the actual result of that frequency responses. Now, so far we know that why we wanted to like actually learn about the frequency response, okay, is because we wanted to like have a steady state analysis, and we don't want to go through all the headaches of running the S domain analysis. Okay, now one thing that we learned from previous discussion is that no matter what type of point we have, what type of state we have, we can always show the value in a state domain, which is the general part of the frequency domain. Okay, the general description of the frequency domain is you can show any point or any state as a vector. That phasor representation of any point in an S. We said any point that we have, any S in an S domain, could be represented by magnitudes and a phase. Right? Now, if that's the case, that means if I have an input, okay, if I have an input, doesn't matter what is my input is, let's say it's S or 1 over S, or even like 1 over S squared plus 1, which was like a sine or something, So either way, if I have a complex number that I can show with a phasor representation, any input would also has the capacity to be shown as a phasor vector. Because the only thing happens, like for example here, is that S is going to be equal to that vector. So this input is actually the vector itself. This one would have some kind of like mathematical derivation, some algebraic mathematical derivation over this complex number, but at the end, the whole situation is also a complex number. Correct? Which means it's also a vector, which means we can show any type of input also with a phasor. Correct? So whatever input that we have, okay, let's say we call our input R, that R of S is also could be shown by a magnitude and a phase, regardless of what the function, what type of input it is. Right? If you know the frequency, if you know the S, you can find the vector that exactly represents that input, which means the phasor that we have. Correct? Now, before we learn that, okay, we are going to have an input when we have a system, any type of system, it could be dynamic or static, and all of them has a transfer function. If we apply our input to our system and we consider the output, like C of S, as an output of what's going to happen to that input in the system, and then we are going to have our observations for the output. This G of S is also a mathematical function over the S, which is a complex number. So on each state, meaning when I say a state, I mean each specific S. Okay, like for example, one state, state 1 could be 1 plus J2, the state 2 could be J3. Each specific S is one state. Are we good? Now, that G of S for each specific state is also a vector, because it has a numerator and denominator. That denominator has several terms. There should be like a summation, multiplication, something of the complex number, and then it would be same thing happening in the denominator. And at the end, you are going to have two complex numbers dividing from each other, which you already know that at the end you are going to have a complex number. The only thing is that how you calculate the general magnitude and phase. So this G of S is also a phasor on that specific state that we can say, okay, it's a magnitude of, with the magnitude of M of G and the phase of phi of G. Are we good so far? Now, what is the CS? We already learned that when we talked about the Laplace transfer. The CS in that system is simply G of S times the input. Right? We already learned that. So this is the R of S times G of S. So if this one is phasor, meaning this is a phasor representation, we have a phasor representation of the input, and we have a phasor, we use dot, a phasor representation of our system, then it makes sense that the output also is a phasor representation, right? And the fun thing is that we have now two phasors multiplying by each other, so the output that we have is also going to be a phasor where the magnitude is simply the multiplication of the two magnitude, and the phase is the summation of the phase. Now, why I'm telling you this, all this stuff. if I can represent any type of output as a multiplication of my phasor input times the dynamic of my system, okay? That means if I could figure out how I can represent the dynamic of the system, that G of S, with a phasor representation, okay, then whatever input I have, I can exactly find, or like easily find, the output based on that input. Finding a phasor of input is easy, is what you have. Okay? Now, in order to analyze the system, meaning you know what's going to happen for each input and find the output, based on what we discuss here, what we need is to find what's happening in our G of S or transfer function or our system. If I can find a way to show this m of g and phi of g, okay, or basically have that in hand, then it doesn't matter what is my input is, I can easily find what was going to happen to that input. Because eventually the output magnitude of that phasor is going to be the multiplication of the input times that transfer function magnitude, the phasor magnitude, and the phase of it is going to be the summation of the input and system phase. So all I need to do is to find this, and then I'm good. Now, in frequency domain, we have a much easier ride, okay, when we talk about the frequency response, because we don't have, our S is purely imaginary, okay? So we don't have real number here at the S. So when we have R of a S, most of the time it's playing with the pure imaginary plus J something or minus J something. Make sense? So it is going to be much easier when you want to like find the phase. Before we use the tangent rule to find the phase, right? Now, most of the time, our variables is purely j omega or minus j omega. So most of the time we are dealing with a plus minus 90. Make sense? Same goes for the amplitude. We don't have to run crazy kind of like mathematics to find the amplitude. It's easier than the Laplace transform or like S-domain analysis. Now, any questions so far? Yeah. When we wanted to like, we said we eventually the analysis would be kind of like shrink down to finding what is the phasor behavior of our system. So what is the phasor that represent the transfer function or the characteristics of our system? If we find that, then we have enough tool to find out what's going to happen in our system based on each individual input. And again, we find out that that phasor, that G of j omega that we had, is basically has an amplitude and a phase. So we need to find out each individual of them, or we can do it all together. Okay? Now, there's two ways. Analyze and represent each individually, or do it all together. What we wanted to choose, which is easier way to do that, is to do that individually. Okay? Now, how to do that when we want to like plot the behavior of our J for each individual omega, because the omega here is a variable, right? If we want to find out how it would behave, that means we have to find m and phi for each individual omega. Does that make sense? Same thing that we did for root locus. We find the poles for each individual k. When k was changing, okay, we want to see what's going to happen to the poles that our system has. Here, we want to find out what's going to happen, what behavior G would have, or what change G would apply to our input. So it would give us the output. But when we wanted to like do that, we have to consider the G, find the M and phi for each specific omega. Because if omega is changing, those values change. Is that clear? Let's say it's 1 over S. That becomes 1 over J omega, right? So it easily can be seen that for omega equal to 1, the amplitude is 1. For 2 is 0.5. You know what I'm saying? So for each individual omega, M is changing. Okay, so we need to like find out what's the dynamic of that phasor based on each omega, so we know if, for example, we have an input at the omega equal to like 2 radians per second, we can look at the phasor behavior, the G behavior at that omega, and find out, okay, what's going to happen to that input. Is that clear? Now, we said one thing is to plot or to analyze each of these two parts individually. When you want to do that, we call that Bode plot, basically. That individual plot or representation of the behavior of the magnitude and phase based on change in omega is Bode plot. And basically, through the Bode plot, we wanted to like represent the M and the phi individually. Let's say this is M and this is phi. This is omega. This is omega. We want to see what's going to happen here. If I have omega equal to 1, my M is going to be, for example, let's say alpha, right? Then that means if I have an input, the output was, the MC was MR times MG, right? So if I have any input, my output for that input would be alpha MR. So it has a gain for the magnet. And if my phase at that specific frequency is beta, that means the phase of the output is going to be the phase of input plus that. So it would actually show us what's going to happen to input and output. If we can represent the dynamic of the magnitude and phase of our system based on change in omega. Are we good so far? Any question? No question? What? Let's run an example to actually see what I mean by analyzing the G and find out what is the behavior of our system is in response to different type of frequency. Let's say the G of S, this is an example, okay? The G of S is 1 over S plus 2, It's a very kind of like simple transfer function to have. Okay? Now, I want to run a frequency domain analysis. That means S is going to be equal to J omega. So I'm going to input that. That means the G of J omega is going to be 1 over J omega plus 2. So far, it's quite clear. Now, normally we don't like imaginary number in the denominator, so let's fix it. So it's going to be the same as 2 minus J omega, and the denominator would be omega squared plus 4. It's the same. I just multiply the numerator and denominator by the conjugate of the denominator. Now, if I want to show this in a phasor domain, how can I do that? Like, let's say, look at it. I can separate the terms. So this is 2 over omega squared plus 4 minus J omega over omega squared plus 4, right? So what is the amplitude? How can I find the amplitude of this transfer function so I could show it in a phasor domain? So I need the phasor domain is going to be the amplitude of this J omega, G of J omega, and the phase should be the phase of that Gj omega. How can I calculate these two? I want to eventually show that in a phasor domain because I wanted to plot magnitude of that phasor and the phase of that phasor separately in order to ease my life later on for analysis. In that specific case, finding the amplitude is very easy. We have a complex number, the amplitude is going to be the square root of the summation of the squares, right? So this part is square plus this part is square, all underneath the square root. That would be our amplitude. Now if you run it, the amplitude is going to become 1 over the square root of omega squared plus 4. You can run the analysis and find out. What about the phi? We said we can use tangent relation, right? The tangent is imaginary over real. So the phi is tangent inverse of imaginary over real. Right? So it easily can be seen that the phi is going to be tangent inverse, actually minus, because we have a minus here, minus tangent inverse of omega over 2. Are we good for that? Any questions so far? No? Now, so far, in order to find out how this specific system would influence my sinusoidal input, sustainable oscillation, sustained oscillation input in a steady state, I find out the frequency domain representation of this system, which is the J omega, S equal to J omega, and then I change it to represent it into phasor representation. Okay? Why? Because I wanted to separate the behavior of the phase and magnet. Okay, now let's work with each other and see what's going to happen to our magnet. This is like 1, 2, 3, 4, 5, 6, 7. Actually, let's do the decade. That's better. This is 1, 10, 100, and 1000 goes on. You're gonna see that. I want to use that for the magnitude, and then a separate one for the phase. If my omega is 0, what would happen to my amplitude? 1/2, right? It's gonna be 0.5. Let's say this is 1, again, 1, 10, 100. 0.5 here. I'm gonna use another color. What about in 1? If omega is 1, what's gonna happen in omega 1? It's gonna be 1 over square root of 5, right? Square root of 5 is 2.1 or something. Is that correct? So in 1, let's calculate that. Why not? Huh? I want to use this example to show you what's happening. 1 over the square root of 5 is actually 0.444. So something right here. A little bit less than that. So far, this is our trajectory. If I put 10, it's going to be 1 over the square root of 14. Right? No, 104, sorry. Which is 0.098, let's say 0.1. So it's here. So now I'm getting down. And if it's 100, it's still going down. So it's trying to touch, and it never gets negative. Okay? So it's trying to touch the 0 one. Very good. This is absolute value, is not decibel or like logarithmic. I wanted to make sure because we are going to talk about that, so don't get confused. I'm using the 1, 10, 100 kind of like unit, but is not the logarithmic values. Okay. Same thing I can do for the phase and find out what's going to happen to the phase. So, for example, in 0, my tangent is going to be tangent inverse of 0, which is 0. So I'm going to start from 0. 1 is going to be tangent inverse of 0.5. What is 0.5? Tangent inverse of 0.5? No, you can calculate. I don't have that in my calculator. So if you have that, you can calculate. But the whole idea is that you can calculate, and it's gonna start, and there is a minus. Okay, is a start to drop, and when the omega goes to like 1,000 or 100, okay, then it basically means the tangent goes toward infinity, which would happen only at pi over 2, at 90 degrees or minus 90. Make sense? So at the end, it's going to end up touching the minus 90 degrees. That minus came from that minus in front of the tangent. Okay? Does that make sense what I'm talking about? So now I have the representation of my system. Now I know if, for example, I apply a sinusoidal with the, with the, let's say, frequency of 1K, I have 1 kilohertz frequency, okay, which means 2 pi f, so it's going to be 6.28 kilo radian per second. So somewhere here, I know that this system would damp that amplitude because the gain here is very near zero. So if I have such a high frequency, my output, which is going to be my input times the mg on that frequency, by say omega equal to 628 k radian per second, which is 1 kilohertz. Okay, on that, this become, let's say the sine was 1 amplitude, but my m of g is quite zero, so it's very close to zero. So eventually my output is going to have zero amplitude. So what did it remind you of? This type of situation? Any circuit that you had in mind that works like that? What circuit, if you give it a relatively high frequency, would damp it entirely? Or low pass filter? See what I'm saying? So now you know you have your transfer function plot and behavior in respect to the frequency, and now you know if I have, like, for example, that input, that means I would have this output. If you want to do the phase one, it's also like this is omega here. If I have that sinusoidal, okay, this system would add a minus 90 degree at that frequency to the input. Make sense? So see how easy it is to use these two Bode plots to find out what is going to be my output when you have any specific input without running all the differential equation or Laplace transform or all this stuff. Are we good? Now, normally, I don't know if you saw that or not, but if you watch for Bode plot, you might be noticed that both plots are drawn in logarithmic or decimal kind of like either instead of like a exact unit of our system. So normally they are represented or plotted in a logarithmic axis or units. Why is that? The logarithmic one would kind of make a lot easier in a way that, let's say we have a complex transfer function. Generally, I want to say is g of s is, I have a k, I have 1, 0 here, another 0, z2, and I can have as much as I want, all the way to zero m. And same goes for the poles. I can have pole number 1, pole number 2, all the way to pole number n. That's the general function. That way, we said if you want to like find the magnitude of the phase that phasor that represent the g, and the phase that the phase of the phasor that represent the g, we have to solve this equation for a complex number equal to j omega. Now that's not easy because you have to now multiply several terms in a denominator. Same goes for the denominator. So you are going to end up in a quite of a situation. So for example, the amplitude is going to be the amplitude of decay times the amplitude of what's happened in the first pole times the amplitude of what happened in the second, zero, all the way to the amplitude of what happened to the last zero. Same goes for the pole. Pole 2 all the way to the last pole. No, I don't want to do that. Okay? If it's me, I don't want to do that. How can I fix that? This is where that logarithmic function would give us a little bit of help. Because when you use the logarithmic function, those multiplication now become summation. Okay? So now you can use that decibel function. The decibel is defined 20 times of the logarithmic of the number, is the decibel version of that number, okay? So if I write it in a decibel way, so is I say the 220 times of the log of my amplitude. Now it's 20 log of all these. What's going to happen is that now these multiplication become summation and the division becomes subtraction in the logarithm. Okay? It's the property of that logarithm, as in the definition of the logarithm. Yes. So now it becomes 20 log of k plus 20 log of the first one, s plus z1, the amplitude of the first one, plus 20 log of the amplitude of the second one, all the way to the last one. And for the denominator, it's just minus in logarithmic. Okay, so it's going to be minus. These all are summation, but they have a minus because of this denominator, so all become minus. Okay, so minus 20 log of first pole minus 20 log of second pole all the way to the last pole. Now, if I show the magnitude in logarithmic unit, that makes my life much easier. Because now I don't need to do all the multiplication. I need to do one term per time and then just add them together. Make sense? Is that good? Now, there is another advantage to this using this decibel too. What is the other advantage? Eventually, you wanted to draw the graph that shows the behavior of this amplitude in respect to change in omega. Correct? So, if I can use the logarithmic way in order to separate all those terms, and the result is the summation of the zeros behavior minus the poles behavior. Okay? What it tells me is that, okay, I don't need even to consider this g of s at the first place. I simply can focus on each term as a different transfer function, find the values, and the overall value would be the superposition of all of those. Does that make sense? So I don't even have to go through the analyzing the g of s. I know these are the terms that I have, so I'm gonna only focus on learning how to find the behavior for this 0, and I'm gonna use the same kind of like analogy on find how is the behavior of like this pole. Okay, now that I know that, I can basically replicate all the other zeros and all the other poles, have different Bode plot for each of terms, and the final part, which is the Bode plot of the overall G, is going to be just adding those plots together. Does that make sense what I'm saying? Make sense what I'm saying? So, like for example, let me do an example that makes like a better case for it. What was the example that we had? Okay. Let's say I have an example where my transfer function g of s is k times s plus 3 over s times s plus 1 times s plus 2. This is my transfer function. And I want to see what's going to happen and how can I basically find out the Bode plots, the behavior of that transfer function in frequency domain, i.e. finding the frequency response of that transfer function. I said I can separate all those terms and evaluate them individually, okay, and then add them all together based on the logarithmic characteristics and find out what's going to happen. So what I need to do is to first solve for, let's say, h1 of s. This is a sub kind of, you can consider a sub transfer function, which is just k. I have another term which is s plus 3. I have third term which is 1 over s, this pole. I have the fourth one which is 1 over s plus 1, and the fifth one which is 1 over s plus 2. Now, when you look at those, you can easily see that they are mostly very simple patterns. Either they are a constant value, they are a 0 in like any place in real axis, they are 1 over s or 1 over s plus 1, like a shift in s in a pole. So either we have k, shift in s, 1 over s, or shift in a pole. Does that make sense? So these two, if you know how to do this one is just the same, just one changed, the 1 changed to the 2. S plus 1 changed to s plus 2. So if you know how to generally solve this, you can also use that for solving this. Same goes for this one, and this one, and this one. Are we good? Now, Let's go over it. What if I have a transfer function with a general form of s plus a this time? What happens if I have such a transfer function? Now, first of all, my frequency domain function would become j omega plus a, correct? Are we good so far? Now, when you want to analyze the system, you normally try to normalize your function. By normalizing function, I mean these coefficients here, a, should be factored out. So the deviation that you have from the origin should be factored out. Then you have a standard kind of like representation. So if you do that, that means it's simply j omega over a plus 1. Not a big deal. Right? Now, what is the amplitude of this function? It's simply a times the amplitude of that whatever complex number that we have over there, or inside the parentheses, right? But let's look at it. I want to simplify it. Here, a is a general number, and my variable is omega. So the relation between the omega and a is very important when we talk about the amplitude and the phase of that complex number. Let me explain more. If a is relatively a small number compared to omega, what's going to happen? The imaginary part would be significantly higher than this one. Make sense? So basically, it doesn't really affect it. Are we good? Now, if a is bigger than omega, then this is very low. We can neglect that, or say it doesn't affect much. And then the amplitude and phase would be dominated by this 1. Correct? So, what that means? That means when I want to find the magnitude of my phasor, I can analyze it by separating the domain into 2 parts. When the omega is less or equal than a, or is bigger than a. If it's less than a, this is a small number, I will ignore that, and my transfer function approximates. Okay, it's an approximation. My transfer function becomes a itself. Right? So the magnitude, the exact magnitude become a. We wanted to show it in decibel. So the magnitude of that t basically become 20 log of that a. Is that good so far? What if omega is bigger than a, then I can ignore this part. So it becomes a times j over omega, a times j omega over a. A cancel each other out, so I have j omega. So now, for this, my magnitude become 20 log of omega. Very simple. How about the phases? if my t is equal to a, what is my phase? It's a constant number. What is my phase? If we are far lower than omega is far lower than a. This is your tangent. Omega is far lower than a. Is a tangent inverse of this low number divided by 1. So it's far less than a is 0. Tangent of a 0, tangent inverse of 0 is 0. So at the far end, our phase is going to be 0. As we approach a, as omega approaches a, now it becomes bigger and bigger, right? At a, it becomes 1, which is what degree? For what phase tangent become 1? 45 degree. So when we have omega equal to a, that tangent started from 0, now it's reached 1. And as we go forward, when omega is much higher than a, it becomes infinity, which is 90. So now the phase of this function, it starts from 0, get to 45 at a, and then increase still all the way to 90, which is when the omega goes to infinity. Does that make sense? Let's draw it. Let's actually draw it. Okay. This is for amplitude. And let's say this is 0.01a. Then this is 0.1a. This is a. This is 10a. And this is 100. Now, for the magnet, we said all the way until a, which is here. What is our magnitude? 20 log of a. Very good. So let's say this part is 20 log of a. So all the way until this line, we have a constant approximation, a flat line equal to 20 log of a. Now, after that, our function becomes 20 log of omega. Now, you can easily see that if you wanted to show your omega on decades, okay, you can simply find out that this is, if omega changes in decade, this one simply become a line with a slope of 20 log per decade. Make sense? So after here, now we have an increasing line where the slope is 20 log per decade. 20 dB actually, log is basically, to be precise. Is that clear what happened? So we approximated the behavior of this term s plus a by separating the domain of omega before and after a and find out what's happening to our magnitude of the phasor domain of our transfer function. Now, as I said, it's approximation. Those lines that we used for approximation would not exactly match the real Bode plot. You can plot that with MATLAB and find it. That you can see that this is not exactly like this, okay, but it's very close. It's a good approximation. The line that we have here, okay, we call it asymptoid lines in a Bode plot. Okay, now the point that the asymptote lines would change direction. So two asymptote lines cross each other. Is that clear? This point, like for example, the line change direction, or you can say this asymptote and this asymptote cross each other at this line, at this point. This point is the break frequency. We call it break frequency. So if someone asks you what is the break frequency, here. What are the asymptote lines? One here, another one here, on this specific case. Now, let's actually do the same thing for the phase so you see how it actually helped for the phase 2. There is a little bit of noise behind this, so let's retard that. Point 1A, this is A, this is 10A, and 100A, and let's say here is 90. These are the points that I know it would go handy to for our description. Now, what we saw from our simplified analysis of this term when we wanted to find out what is the behavior of the phase of the transfer function, we said when we are we have omega way less than a, so this term is neglected. This is 0 basically. We have t of s equal to a. We have a 0 as a phase, right? So here at the very end we have a 0. We set as a at a when omega is equal to a, we are reaching to a very specific point when the tangent is equal to 1, meaning the phase should be 45 degrees. Correct? At a, we are at 45. And when omega is much higher than a, like in those infinity part, we said we don't have any constant. This is tangent of infinity. Tangent of phi is equal to infinity, so tangent inverse of infinity is going to be 90. So we are going to end up somewhere here, right? Now, on the phasor graph, we have a little bit trickier situation than the magnitude. In magnitude, we just draw a line and we're good. But here, if you look at it, this initial point, which is 0, happens in a much small omega. But when you can consider the omega large enough so you cannot now ignore the imaginary part here. The rule of thumb is the order of 10. we consider omega much smaller than A if it's more than 10 times small. When we reach the 10 times, then it's not very kind of like a good approximation to neglect that. So up until here, we are good to assume that omega is very small and we don't have any phi. It's zero. So up until here, we are good. Same goes for the other side. Here we said omega is much bigger than A, so we have tangent of infinity. Now, where we draw the line of that much bigger condition? Again, 10 times. So we say if omega is bigger than 10 times of A, we consider it as a much bigger, so we can neglect the constant part here, the one part here. Does that make sense? So after this point, after omega exceeding from that 10A, we can consider the second assumption and say there is no one here, and we are at 90 degree. Make sense? So this 90 degree can come all the way up until the 10. Now, what's going to happen between the 0.1 and 10? He said we are going to use a simplified version, or as we call it, asymptote lines. So what we are going to have is simply a line that connects these points, which by the look of it, you can see that the slope is 45 degrees per decade. See? 1 decade, 45 degrees. 1 decade, 45 degrees. So now you have the graph for S plus A, for both magnitude and phase. Now, the first term that you have here is S plus 3. Just put A equal to 3, and you have your graph. Are we good? Now, what we need to do in order to finalize everything is to find what is the graph for 1 over S and 1 over S plus A, so we know what to do with these last 3 points. Now, this is, I think we are running out of time for today, so I'm not going to start the rest of it. Okay? Just one thing for the K, because it's very easy. Okay? It's not a function of omega, it's constant number. So it's very easy to know that the magnitude of a constant number, the behavior of that magnitude of the constant number, is going to be constant, because it's not changing by the omega. So the Bode plot for this, the Bode plot for the magnitude, regardless of the omega, is going to be a constant number, and that constant number is what? 20 log of k. So 20 log of k. What about the phase? Again, it's not a function of omega, so you want to change. It's still a flat graph. But what is the phase of k? It's a constant number. What is the phase of k? If you want to represent this k as a complex number, what would be? What is the complex number equal to this k? K plus 0j, right? So if the 0j, that means the phase is 0. So it's always 0, no matter what. So far, we have these two, correct? So far, if we didn't have these poles, okay, the transfer function plot the general transfer function, if we didn't have these poles, would be simply for the magnitude this one plus this one. It's a constant number, meaning it would just shift the whole plot 20 log of k, and the phase is 0, so the phase still would be the same. If we didn't have any pole, the general transfer function would be the summation of these graphs, right? For the magnitude, it would be 20 log k plus the plot that we have here, which is a shift. For the phase, it doesn't change anything, so it's going to be the same phase at that s plus 3 that we have. Is that clear? Now, in the next session, we are going to talk about these type of terms too, to find out how these would behave when we want to draw the both plot and both for both magnitude and phase. And when we know those, that means it doesn't matter what type of or how complicated the transfer function is, as long as we know the terms that would create those transfer function, poles and zeros, we are easy to do. We just have to draw those poles, or even like have those poles ready, like you have the graph for s plus a, and then you just add them together and put the a's based on your transfer function. Same goes for the poles. Any question? Okay, that's it for today. If you don't have any question, we can finish the session by now, and have a great rest of the day.